Right, I think this will be the last video of our Unit 3 practice test problems. Went over 1 through 16 so far. In this video, we will go over number 17 through, let's do it all, up to 21, okay? All right, number 17 is a graphing problem. I'm giving you that the below is a graph of f of x equals log base 0.25x. We want to move this. We want to describe the transformation and translate it to become the graph of. Now take a look, at least we got the common base. It's the same exact function, right? But look at what we are doing to this log base 0.25. We're subtracting 4 inside. And what else are we doing outside? We're adding 1 outside. So remember the transformation rule that we went over in the very first unit. Adding 1 will shift the graph, move up 1 unit, right? Every point on this graph will go up 1 unit. What else? This subtracting 4 inside will move 4 to the, which direction? Right. So what we're going to do is this. If you guys are taking this exam on Alex, then it will be as easy as just you grabbing this graph and dragging it, okay? Up 1, right 4. But for me, because I have to graph this by hand, I will just pick some good points here, okay? First, now take a look at the vertical asymptote of this graph. If we have a vertical asymptote at x equals 0, okay? Before any kind of horizontal translation, we have a vertical asymptote at x equals 0. Removing this horizontal asymptote, I keep saying vertical asymptote 4 to the right. So the new vertical asymptote will be at x equals 4. This is going to be the vertical asymptote of g of x. And this one is, the purple one is the vertical asymptote of f of x, right? You notice why it moved 4 to the right, because we're about to shift our graph 4 to the right. And moving up, you know, it's a vertical line that goes up and down forever. So moving up doesn't really matter here. But let me go ahead and plot or find some points on this original function, okay? So the original function looks like I have a point right here at 2 and a quarter point, I think. No, 2 and 1/2. And then another one over here. And then I think I have another one right here. I'm just trying to do as many points as I can. All right, so I picked my 4 points that are just on this graph. And what you're going to do for me on this exam is really the same thing. Just pick enough points. And then we're going to move these 4 points according to this direction. Move up 1 and move 4 to the right. I'll do this one first. But what is 1 in this graph? We got to look at the scale of this graph very carefully. This is 1, 3, 4, 5, 6. This one is -1. So every 2 boxes is going up 1. So I'm going to go up 1 over 4 to the right. 1, 2, 3, 4. I'll be outside the graph, but that's okay. I have my first point right there. Let me do the other one. Up 1 over 4. 1, 2, 3, 4. Here's my second point. Now, I'm sorry, the graph, this is not going up by 1. Like the grids is actually is going up by half. So that was a little bit confusing, but that's okay. Next one, I'm going up 1, same thing. Up 1 over 4. 1, 2, 3, 4. So the new point is at 8, 0. And the last point, I'm moving this 1 up. 1, 2, 3, 4. So here it is. Now, I'm going to go ahead and graph this function. This is going to go down that way. And then it's going to go up, but it will get really, really close to the vertical asymptote at x equals 4. But it will never be able to cross the vertical asymptote of x equals 4. All right, so we graphed it using 4 points. We're going to state the domain of g of x. Now, notice this graph will go on to the right forever, but we do have a vertical asymptote on the left bound. So the domain of g is going to be from 4 to infinity, where we're not going to touch 4, so do not do bracket 4, okay? So this will be incorrect. It should be 4 with the parenthesis in front, because that's where the vertical asymptote is. And that's going to go to the right forever, so right, positive infinity. Now, what about the range? Remember, exponential function's domain is all real, so its inverse function, the logarithmic function's range is going to be always all real. I know it kind of looks like it's slowing down, but it's going to go down forever to the right, and it's going to go up as it gets really, really close to x equals 4 on that side. All right, find the asymptote of g. Well, we already found it for them, right? We have a vertical asymptote at x equals what number? 4. And that was based on the horizontal translation of moving 4 to the right, right? All right, so that's that. We're done with that one problem. All right, so let's go to number, why isn't it moving? Let me try to close this app and try to reopen this app. Come on, app. Okay, let's look at number 18 together. It's a word problem. Suppose that $50,000 from a retirement account is invested in a large cap stock fund. I remember this problem. Wasn't this from your Canvas quiz that I asked you to complete for 3.6 lesson? This is a good problem. After 20 years, the value is $134,561.72. It grew a lot in the last 20 years, huh? They want you to use the model A equals P times E raised to the RT power, so the continuous growth function, to determine the average rate of return under continuous compounding. They want you to find the rate here. Okay, all right, let's find that rate. So plug in everything we know. A is $134,561.72, and the principal, the original investment amount, was $50,000. Now T is 20, right? 20 years. Now we don't know what R is. That's what we're trying to find here. So let's plug in everything we know. 134,561.72 equals 50,000 getting multiplied by e to the 20 times R. Let's divide both sides by 50,000 on both sides. 50,000. So, you know what? I'm going to keep this fraction. 134,561.72 divided by 50,000 because I'm not going to round it in the middle of a problem. E to the 20 R power. Now, what will you do to both sides at this point? Okay. At this point, what we're going to do is we're going to take natural log of both sides because when you have an exponential term with e as the base, taking natural log, we'll get rid of e and we'll bring down the exponent, the power of 20r. So natural log of 134,561.72 divided by 50,000 equals, well, natural log of e raised to the 20r, right? But remember what happened to this natural log of e. That's just 1. So we're gonna, I hate writing this big fraction, but it is what it is. So let's just write it one more time. Equals 20r. So what's that? Well, all we need to do is divide by r. And I will make sure to give you more room for the paper pencil exam takers so that you can write more work that is not squeezed, okay? So let's type this in. Divide natural log of 134,561.72 divided by 50,000, and divide that number by 20. R comes out to be 0.0494999. Now, how did they want you to round? They want you to round to nearest hundredth of a percent. Now, they want you to round it to a percent. So multiply that answer by what? 100. And that turns into, let me go ahead and write down the answer. This is 4.95%. 4.95% rounded to nearest hundredth of a percent. Okay, so we found the rate. Now, what do they want for part B? How long will it take the investment to reach $250,000? Okay. So $250,000. So million has 6 zeros. If you divide 1 million by what? 4. What we want is A to be 2,500,000. Okay, that's $250,000 right there. So what we want is that A. Well, we know that P is 50,000. The initial investment is still 50,000. And what we know is that R is equal to 0.049. Or 95. Okay, we just want to find what T is. How long will it take for this investment to grow into $250,000, right? So let's go ahead and plug in these inputs into our equation. Equation is $250,000 equals $50,000. We're starting from 50,000 times e to the 0.0495 t. We're solving for time this time. So same kind of math. Divide both sides by 50,000. Divide by that constant. So what is 250,000 divided by 50,000? That gives you 5. So we're trying to get 5 times our original investment. 5 equals e to the 0.0495t. Now what do you do to both sides? Now take natural log of both sides. Natural log of 5 is equal to natural log of e raised to the 0.0495t. And then as you can tell, this natural log expression is now gone. We're going to have natural log of 5 equals 0.0495t. Therefore, t is equal to natural log of 5 divided by 0.0495. You guys did this problem for me on your last week's classwork. So just a review. If you go ahead and type this in, you will get 32 point. Now, how did they want you to round it? Nearest tenth of a year. So what I got was 32.51. So let me just say 32 years and 32.5 years. I wish I can just move this a little bit over so that I can write the unit, not 35 days or not 35 seconds, but it's going to take us 32.5 years. So that's how you will solve it. You know, the solving equation was really the same thing, taking natural log of both sides, dividing by the coefficients. But we just have to make sure that we label everything carefully in these word problems. And I will have one just like this. I'll even keep the wording the same. Just change the rate and probably the amount, maybe the time, and have this one again on your exam, okay? All right, let's graph number 19. Graph g of x equals 4 to the x power. Now, you guys have a graphing calculator, so if you want to graph it using your graphing calculator, that is okay. But I'm going to go ahead and just do this by hand, because I know you can too. So let's go ahead and graph y equals 4 to the x power. So x, you know, it would be nice to have a couple positive and couple negatives, and I'll have all of those too. How about if I have, like, start at 0, 1, 2, and 3? It's going to go up pretty quickly, so I may not be able to plot everything. So if you raise 4 to the 0 power, you will have 1. Anything to the 0 power is 1. 4 to the first power is 4. 4 squared is already, 16. And 4 to the third power is going to be 64. So, not too many. It's a very, very rapidly growing function. So I'm not going to be able to plot 364, but I'll be able to plot 0, 1. And what's the other one? 1, 4. And then 2, 16, maybe not really. So what I'm going to have is a right end going up like crazy. So the right end behavior is approaching positive infinity very, very fast, right? The base was 4. All right, now what about if I take couple to the negative? What is 4 to the negative first power? That is positive 1/4, right? That is going to be a quarter. So at -1, I am about at a quarter point. And then at -2, 4 to the negative second power, that is 1 over positive 16. And that's really, really getting close to 0. But remember, when we graph these exponential functions together, they will never go to 0. It's going to get really, really close to 0. But what do we have? We said that we have what kind of asymptote? That red line that I'm sketching right now. We have a horizontal asymptote at y equals 0. Now think about this. As we get smaller and smaller, as the x value gets smaller and smaller, what we are doing is we're dividing the number by 4, right? 64 divided by 4 is 16. 16 divided by 4 is 4. 4 divided by 4 is 1. You're dividing by 4. So keep on taking 1/4 of a previous number. You keep taking 1/4, 1/4. You're getting smaller and smaller and smaller. But will you ever be able to become 0? Will you ever be able to go down to negative? And the answer is no. So we have a horizontal asymptote at y equals 0 for this function. Is g one-to-one function? Well, remember, exponential function has inverse function. the logarithmic functions. So is this one-to-one? Yes. They have inverse functions. And you see all the y values are has a different input value. So yes, this is a one-to-one function. Write the domain and range of G in interval notation. All right, let's go ahead and give them the domain. Domain is going to be from negative infinity to positive infinity. This is a exponential function. So exponential function, you can plug in anything into the exponent. We'll be able to evaluate it. Now, what about the range? As you can see in the picture, it's not going to go below that line 0, right? In fact, it's not even going to touch the line at 0. So the range is from 0 to positive infinity. Now, what they want you to do is graph G inverse on the same coordinate system as G. So what I'm going to do is I'm going to go ahead and create G inverse XY table over here. And I'm not, I was only successful plotting about like 3 points here. So I'm just going to go ahead and copy those 3 points down. And those 3 points were 0, 1, 1, 4, and maybe this one. All right, so if x is 1/4, I'm going to have a y value of -1. And you know how I'm getting this, right? I'm just flipping x and y. When x is 1, the y will be 0. And when x is 4, the y will be 1. We can evaluate the logarithm. We can rewrite this as G inverse of x equals log base of 4 of x. We can do that, but that's going to give us the same XY table. You can just switch x and y, right? So let's plot these points. 1, 0 is up over here. 4, 1 is going up here. And then the last one, quarter -1 is going to be over here. All right, let me go ahead and grab a blue highlighter. And then this is going to go up forever. And then this is going to go down to the left side like this. But it will not be able to cross that vertical asymptote of x equals 0. So this graph has a vertical asymptote at x equals 0, and this is for the G inverse of x, okay? Write the domain and range of G inverse of x in interval notation. Domain is going to be from negative infinity. Oh, no, I'm sorry. Domain is going to be the range of the exponential function. So notice how far does it go to the right? I mean, it's trying to get to 0, right? But it's going to go to the right forever. So the domain is from 0 to positive infinity. Now range, you know what I'm doing? I'm kind of cheating over here. I'm looking at the domain must be the same as the range of the G, and the range of this G inverse must be the same as the domain of the original. So keep, that ideas keep coming back, the inverse function idea, the domain and range. So that's it. We got it. Now they want you to evaluate G inverse of, a couple evaluating problems. We'll do that. G inverse of 1/16, G inverse of positive 16, and G inverse of 1. Now, we never really officially wrote this blue logarithmic function with base 4 yet, but I can evaluate a couple of these. Like, for example, this one right here, G inverse of 1 is 0, right? I didn't write G inverse of 16, but we know what x value had a y value of 16. And when x was 2, y was 16. So if I want to create another one, I can have 16 and 2 over here. So the y value of the inverse function will be the x value of the original g of x. So that will be 2. And this one, what x value had a y value of 1/16 in our original function? So I'm really using the inverse function, the original function, to evaluate these inverse. Which one had 1/6 as the y value, 1/16 as the y value? And that one was -2. Now, if you can, I mean, of course you can actually write the logarithmic function. The G inverse of x is log base 4 of x. And you can plug in these values if you want. Log base, starting with the easy one. Log base 4 of 1, if you type this in your handy dandy calculator, it will give you 0. And the other ones too, you can go ahead and do what's the log base. Why am I putting 2 in there? But if I were you, I would just use the xy table from the original function. 16, that will be log base 4 of 16. And what's that going to be? That's going to be 2. So similarly for the first one too. That's what you can do to evaluate. I would definitely use the XY table, okay? Because they're not giving you some crazy values. They're giving you the value that we kind of saw on the original XY table for the g of x. All right, I got 2 more word problems, and that's it for this practice test. I just had to give you some because you guys did a lot of word problems in this unit. Many applications of exponential and log functions. Number 20, suppose that $13,000 is invested in a bond fund and the account grows to, wow, $13,698.08 in only 5 years. Oh, well, I said wow, but really only grew about $700, but that's still something in 5 years. Okay, so use the model A equals P times ERT to determine the average rate of return under the continuous compounding. Round to the nearest 1/10 of a percent. Avoid rounding in intermediate steps. Now, guys, don't you think this is very similar to number 18, where we did the large cap stock fund? It's really the same exact thing. You know what then? I'm going to ask you to try number 20 and 21 on your, well, 20. I'll say try number 20 yourself. Okay? And I'll make a note similar to number 18. So I'll go and check both your Alex exam and your paper pencil exam. I think I have a duplicate of a problem because these are very similar. Yeah, I may take one of them out. I'm gonna keep that large caps, then. But this is gonna be a very good practice problem, number 20, similar to number 18. But let's do the last one, number 21. I haven't done any logarithmic application problems, so here we go. A company spent X $100 on an advertising campaign. The amount of money in sales, S of X, in thousands of dollars for the 4-month period after the advertising campaign can be modeled by this function. All right, if the sale totals $18,600, how much was spent on advertising? Round to the nearest dollar. So what did they just give us? They just gave us the total sales amount. So S of X equals 18,600. Let's plug in 18,600 on the left side of that equal sign. And what are we going to solve for? We're going to solve for X. And X stands for the hundreds of dollars on advertising campaigns. So how much money did they spend? Let's find X. Subtract 4 from both sides. 18,600 minus 4 is 18,596. 7 times natural log of X plus 1. I'm going to try to divide this on my calculator. It wasn't too nice. See, the next step is to divide both sides by 7. And if I do that, I get a nasty looking decimal. So I'll just leave it as a fraction, okay? And that's okay. What do we do now? When you're trying to solve an logarithmic expression, like equation here, we got natural log, right? You're going to have to rewrite this in exponential form. So what's the base here? The base is E. E raised to the 18,596 divided by 7. And that equals what? X plus 1. So the exact value will be X equals E to the 18,596 divided by 7, subtracting 1. But if you tell your boss, hey, we spent this much money on advertising, that's not going to be good. So let's give them the decimal of it. Let me go ahead and type this into my calculator. E raised to the 18,596 divided by 4. And then we're going to subtract 1 from it. Overflow error. Are you kidding? Oh, really? Oh my gosh. No worries. You know what? I made a mistake. You know what my mistake was? Oh, thank goodness. The S of X is in thousands of dollars. So I don't have to use 18 point. Oh, thank goodness. I'm not going to use 18,600. Why don't I plug in 18.6? Because 18.6 thousands of dollars is 18,600. So let me fix these numbers, okay? Change that 18,600 to 18.6. Thank goodness I caught that. I'm sorry. And I honestly caught it because my calculator said overflow. Because it was too big. 18.6. Oh no, everything kind of changes. Let me just restart again. read every word very carefully. Okay, so we're setting it up as 18.6 equals 4 plus 7 times natural log of x plus 1. Subtract 4 from both sides. 18.6 minus 4 equals 14.6. And then we have still 7 times natural log of x plus 1. Divide 14.6 by 7. It doesn't really come out too nice. So I'll just say 14.6 divided by 7 equals natural log of x plus 1. Now what? This is where we rewrite this in exponential form, right? E to the 14.6 divided by 7th power equals x plus 1. Therefore, x is e to the 14.6 divided by 7 minus 1. And let me type this in my calculator. So we did it right this time. First, my mistake was that I used that 18,600 as 18,600, but they wanted the S of x to be in thousands of dollars, not $1. So e to the 14.6 divided by 7. And if I subtract, oh no, I typed it in wrong. 14.6 divided by 7. And then if I subtract 1, I will get 7.0503. And let's see how they want you to round this. Round to the nearest dollar. No way they spent $7 on an advertisement. What was the unit for X? Let's see. X is in hundreds of dollars. Aha. So what do? We do 7.0503 times 100 because X was in hundreds of dollars. So they spent about let me put the unit. They spent about $705 on advertising. That's what it is. It was kind of tricky just because of the units were in different dollar amount. But other than that, solving for it, setting it up, wasn't too bad, right? So that's it. That's really it for this practice problems for exam 3. I decided to keep your paper pencil exam to just 20 problems. And I'm going to try to go in and take a look at your Alex to remove any duplicates so that you can spend more time on each of the problems. And that is it. Really, that is it. And then, well, I do want you to email me if you have any questions on any of the problems that we just went over together, okay? I will look forward to your